Just going to start in a minute for anyone tuning in. It's our week 11 lecture. I know week 11 doesn't always seem like the most exciting week, but I've got some fun stuff to show you and chat about today, so I hope you're joining me. Where's my little control pad? Uh-oh. G'day folks, how you going? Just about to start week 11's lecture. I think I might just close my door. I do try to keep start my recording. G'day again, I'm going to turn my lights on. How about that? 1, 2, I do look a lot better when the lights are turned on. Welcome to week 11, everybody. Another lecture online, live streamed. Feel free to send me any questions or ideas or anything you think of during the lecture in Teams. It's always great to have your comments as we're going. I will say that I'm not sure if there's any background noise. Someone is using a circular saw or a grinder or something next door, so I don't know what's going on with that. Hey folks. Yes, we are back in week 11. Now I know Ben was just saying, oh, are there actually lectures in week 11 and 12? There are lectures in week 11 and 12. I know everybody is working on their major projects, and it seems like why would we need more content, but this is a good chance now that you're focused on your project to tell you about some kind of, I suppose, extra information, things that might be a taste of what you might see in a second course in Art and Interaction in New Media. We don't have comp1720 part 2, but I can at least give you a taste of things that you might like to investigate on your own. It also might be something that you might find some inspiration for in your major projects, or find that you can integrate some aspect of this. I don't know, but I'm just going to keep talking to you about stuff because, you know, our lectures are not just a way for you to get information that's implemented directly in your assessments, but it's a nice time that we can spend together each week talking about art and interaction in new media, talking about P5, talking about interactive art, and we like doing that. So we're going to do it today. You'll have a lecture with Tony on Friday. We will have lectures in week 12. I will be lecturing on Wednesday. Tony will be lecturing on Friday, the last day of week 12. So last teaching day of 2020. Tony will be there talking about art, as he always is. Today's topic is simulations and dynamics. But before that, we're just going to do a little bit of admin corner, or I suppose positive affirmations about your major project. Now, everybody at home, you know, take a deep breath in and repeat with me, I have started my major project. I have started my major project. I have committed my latest work to GitLab. I have committed my latest work to GitLab. I have been adding to my SOO as I go. I have been adding to my SOO as I go. I have looked at my major project at the test URL. I have looked at my major project at the test URL. I have looked at my major project at the test URL. When I need help, I ask on the forum. When I need help, I can ask on the forum. When I need help, I ask on the forum. Now, don't we all feel better now? Having these positive affirmations about our major projects. I know everyone has done these things. If you haven't done any one of them, today will be the day to do it. I think that I think that everybody has made a lot of progress on their major project concepts and implementations in the last 7 days since last week, when I told you folks that you had to start your major project. I'm just getting a message from Brent on my thing. Oh, I see. Lecturing them. Brent's just sending me random messages during my lecture, which is not helpful, I guess. You've been working on your major project this week in order to give or discuss a sketch of it in your lecture. I was really happy to start seeing these sketches come up on the forum, and the reality is you can keep doing that. I want you to do that again next week. The difference with next week is that there are no more visual diaries. You don't have to do a visual diary for week 12, but if you want to show something off or get some ideas, post about it on the forum, ask people what they think. And there are a few of you who are really, really good at it. I really appreciate you being there, because everything you say on the forum, other people get benefit from. But anybody else, if you do have ideas, you want to check with people, or new or coding concepts that you're unfamiliar with or finding difficult, get on the forum, ask a question. Everybody will be there to help you. I think Alfred is like the best forum answerer ever, so he'll be in there talking to you about what you're doing. What next? So I've got a little bit of details about major projects each week until the end of the semester. So this week we're just going to talk a bit about process and policies for the major project. The process is the same as the assignments. You have a very clear understanding now about how to submit assignments in this course. You must add an interaction statement and an artist statement in your major project. If you leave them blank, there will be a significant loss in marks. We don't accept late submissions in this course, so make sure that you have your major project in GitLab, uploaded, committed, and pushed on time. Don't forget about time zones for anyone outside of Canberra. Make sure you know what time it is in Canberra and you know what time the major project is due. And in an extra part of no late submissions is I know there are people who have things that go wrong in their life related to health, their well-being, their personal situation, things that mean that they need more time for an assessment. I'm always happy to discuss these matters with individuals, but I need to know about it well before the assignment is due. And if anyone gets to the last 3 days that the assignment's due and they think, oh my goodness, because of my personal organization, I haven't got an assignment to hand in, then that is a very big problem for you. So if you think that you do need an extension for any reason, get in touch as soon as you can. Don't leave this until the last minute and we can discuss it. If you are asking for an extension at the last minute, then I will be requiring proof, as in like a medical certificate or proof of your situation, explaining why you need an extension. This can be considered the exam for this course, so it's very important that we kind of have a clear understanding of the deadlines, a clear understanding of these processes, because it is worth 50%. Finally, make sure you reference everything in your statement of originality. We had assignment 3 go in. There were a few people who had a blank statement of originality and yet they had assets, code, or clear inspiration in their repo, where myself and the tutors could obviously see that they were using an asset from the internet, and yet it wasn't in their statement of originality. At the university, we expect you to cite all work that's included in your assignments, which is not yours, okay? Those folks will be having a chat with me before they get their assignment 3 marks back, and we may be having an adjustment of the marks related to that situation. You can't afford to have these things go wrong in your major project, so make sure that your statement of originality has everything there. Reread the academic integrity policy. By and large, folks have been really good about their SOOs. I really like it when people are on the forums saying things like, oh, I found this thing on the internet, but I'm wondering if I should put it in my SOO. And the answer is always, yes, you should totally put it in your SOO. So please go ahead and keep asking and I will keep saying yes. I will keep showing you ways to put things into your SOO if you're unsure about it, but don't leave it to the last minute. You still have a chance to get help in your week 12 lab. There's one more lab in this course. This is not a write-off lab. Your tutors are there. The only thing they're there to do is to hear you tell them about or show them your major project and give you feedback about it. The best way to use this lab is to have your major project pretty much done and show it to your tutor and then edit it, because a finished major project is really, it's not really finished until you've shown it to someone else and had them give feedback, you've had a chance to update it. The programs are generally not finished the moment you sort of put the last semicolon on the last line. They're finished when you've tested it, you've had a play with it, you've thought about it, and you've been able to adjust, fix little things that you couldn't fix before. There's nothing wrong with showing off your major project on the forum if you're comfortable doing that. So if you do want to get feedback from everyone in the class, put it on the forum. Now, a few major project tips. Most of you will have seen things related to this before, but just to go through these one last time. Sketch. It's not too late to try different angles. If you are struggling with something in your major project, make some little extra p5.js ideas. I really like using the peditor.p5.js.org. I'll be using it today, just to sketch out little ideas. Oops, I should be making myself small really, shouldn't I? Sketch out some little ideas. Oops, new. Here's my crap idea. There we go, a circle on a gray background. That's a bad idea for a major project, but maybe you can take that somewhere. editor.p5js.org is a really great way just to sketch things out. Do some user testing. Make sure you do show a friend. Do show your tutor. Don't tell them anything about your major project and just see what do they do with it. Because I see a lot of concepts with major projects that rely on some kind of game mechanic. You're supposed to press certain buttons or use the mouse in a certain way. And often when you're designing something, you don't realize how hard it is for someone else to actually understand what you're supposed to do with an interactive work. But if you show it to them, don't say anything, just give them send them a link or send them, turn your laptop around and let them play with it. See if they do anything strange you didn't expect, see if they can actually figure out what you want them to do. And that will really help you to understand how to improve your project. What's the wow factor? Can you figure out something about your major project which is going to make people go, wow? What's the thing which is going to draw their eye? I want you to particularly think about the wow factor in terms of just seeing it on the wall in a gallery. What makes your project appealing, even if someone's not interacting with it? Because when I'm grading them, I will put it on the screen and just look at it without interacting first, and then do the interaction. So I want to see if there's something about it without interacting that actually draws me in, rather than me having to start interacting to see the project unfold. Make sure you're writing your SOO as you go. We've talked about this before. Push to GitLab all the time. I know you've all started pushing to GitLab. Make sure you continue pushing to GitLab. Make sure you're pushing to GitLab every single time you have a work session on your assignment, not just at the half an hour before the deadline. A few rookie mistakes. These folks don't look like rookies. They look like experienced soccer players, but we can all be rookies sometimes. Not reading the spec. Make sure you read the spec. This is a very serious assignment, 50% of your grade. Read and reread the major project page. If there's anything unclear, ask on the forum. Making a game. I've talked about this a lot. The tutors have talked about it a lot. It was in the labs this week. Where's the artwork in a game? Well, some games are very artistic and some artworks have game elements, but make sure you're making an artwork and not a game. Make sure that your artwork communicates something and doesn't just try to engage in a sense of kind of achievement of meeting goals, right? The communication is not always the same as meeting a goal. Ask yourself if your artwork would make sense on the wall in a gallery, not as a game that someone has put onto their PlayStation just to get going with. Not testing at the test URL. When I grade them, I don't use the test URL, I get your Git repo. But if you're going to the test URL and the test URL works, you can be very confident that your assignment will work on your tutor's computer and on my computer when we're giving you grades for it. So the test URL is also how your friends are going to look at your artwork when we put it into our end of semester gallery. And it's your best way of just double checking that everything is working. If things don't work at the test URL, ask on the forum if you can't figure it out. Another rookie mistake, putting an example in the microwave. There's lots of examples available online of bits of P5JS code. You might have done a few increments on an example available online for an assignment, and that might have been okay. But this is not enough for your major project. So make sure that you do have enough new content, enough thought, enough iteration to make sure that your work is uniquely yours, and worthy of a major project submission. Conceiving of the theme too narrowly. I think this is, can be a bit of a danger when people are not comfortable with coming up with lots of new ideas for an artwork. Think big, think broad, think outside the box. Make sure you use your artist statement to tell me how you interpreted the theme. I'm getting a bit worried. There are some folks saying on the forum and in their labs, oh, the theme of my assignment is the pot calling the kettle black. I'm like, well, hang on a minute. Isn't the theme of the major project fearful symmetry? So that's not the same. And then they say, well, the pot calling the kettle black is something, but I'm telling that about relating that to fearful symmetry. And I'm like, well, now you've got two themes. This is very confusing. Why do you need two things? So make sure you're focusing on the actual theme of the major project. Make sure that your conception of the theme is big, broad, outside the box, creative. Keep iterating on that idea, and then explain what you've done. Explain in your artist statement how your theme is, how you've interpreted the theme. And very finally, don't make a PowerPoint. So this was a bugbear of Ben Swift, a former lecturer in this course, but I know what he means. By a PowerPoint, I mean maybe a major project which has 3 different scenes assembled on the screen, and you click anywhere on the screen to get to the next one, and then you click somewhere and you get to the next one. If it's something that could be made in PowerPoint better than in P5.js, then it's probably not an interactive artwork in P5.js. It's probably a PowerPoint presentation. So just be a bit careful. It's sometimes hard to avoid this if you've got a very structured idea for a story in mind. So I would suggest that you sketch your idea, show it to your tutor in week 12 and this week, and make sure you find a way to reduce the scope, because the more story elements you're trying to combine, the more scenes you're trying to combine, then the less you can focus on interactive artwork aspects of it. Okay, that's enough talking about the major project. We're going to talk about some fun other stuff, code theory. This week's topic is taking inspiration from nature. And what do I mean by that? I mean things like movement, friction, force, fields, growth, reproduction, decay, collaboration, ecosystems. So these are all things that change in nature. Systems that change, systems of cells, of objects, of forces, of interactions that change over time. So the goal of the programs in this lecture is to simulate these kind of systems and explore dynamic and emergent behaviors that we see in them. This is a really great way to make interactive artworks or computer artworks. It's something that people have done for many, many years. The idea is looking at representing some kind of natural system, either like objects in the world with physics, or life forms or animals, doing some kind of bio-inspiration, then modeling it in a simple system and seeing what happens. And usually what happens is fun, interesting, compelling, artistic, and worth doing. So the reference here is a book called The Nature of Code by Dan Schiffman. Most of you will have seen some of Dan Schiffman's YouTube videos during the semester that I've been linking to. This is kind of a textbook for a second course in creative coding that you might take after comp1720. It's available for free online, or you can pay what you like for it as a PDF. You can also just look in the P5.js examples. All these ones under Simulate are really just examples from this book. So you can look at that to get the same idea. So note well, this book uses processing, not P5.js, processing being the Java implementation of the same idea of P5.js and kind of the predecessor of P5.js. So I've got 3 little examples to talk to you for the rest of the lecture. First one's vectors and physics. Second one's kind of this cellular automaton called the game of life. And the third one is flocking and voids. So first one, vectors and physics. I think we talked a little bit about this before. I'm not quite sure. Everything before the baby arrived is like a distant blur in the distant past. I can't remember it. I've got a little pattern in this lecture. Who invented physics? Well, lots of people invented physics, but we often think of the originator of modern physics or our modern understanding of things like gravity and movement as Isaac Newton, born 1642. So a very famous scientist. We often call that like Newtonian physics, what he invented. And I guess what we're going to do is related to that, or it uses Newtonian physics, of course, but it's not like the kind of high school implementation. where you're learning some formulas and applying them to arbitrary situations and imagining when a ball is going to hit the ground. We're just going to sort of start hacking intuitively and see how that goes. So we're going to simulate motion. I think many of you have tried this out. We're going to simulate realistic motions by using simple rules of motion. The easiest way to do this in P5 is to do it in 2D. 3D gets a little bit wacky. And we're going to use an object called p5.vector. So this is an object that wraps up an xy value. You can have a look in the reference if you like. But the way you use it is that if you want a vector, you can use this create vector command, which you can just put anywhere in a P5.js sketch. Then when you've got your vector vec, you can access the x value with .x and access the y value with .y. I guess you might ask, well, why don't I just use a normal object or an array to have a vector? Well, you certainly can. It's a good idea. The reason to use a P5 vector is that they provide you with lots of methods or functions to do with that, which can be really useful. For instance, if you want to subtract one vector from another, multiply vectors by a scalar, divide vectors by scalars, find the magnitude or length of a vector, magnitude squared, which is handy, do the dot product of two vectors. If you're into vector maths, you'll know what that means. If you're not, don't worry. Cross product of two vectors, even more weird vector math. Work out the distance between 2 points. So it's got the vector object in P5 has a lot of extra machinery built into it, which is useful. We're not going to use it right now, but just good practice. If you're doing some 2D motion stuff, maybe you want to use p5.vector. So we're going to make a model of a bouncing ball. That's my plan for today. So I'll have a variable ball. This is my little skeleton. And then I'm going to make a ball object, which is going to contain all the information about a ball, as well as some functions for doing things with it. So I think I told you in our objects lecture that you can add functions into an object, which is a cool idea because then that object can kind of do things itself. So our ball is going to have a position, that'll be a vector. It'll have a velocity, so it's constant amount of movement. Yep, Ben Cusack is saying, oh, two people in there saying, I wish I had vectors. Ben is saying it's useful to be able to rotate vectors. Very, very useful. In fact, crucial for one of the examples I'll show you later, although I won't do it. The code gets a bit chunky to do everything in the lecture. But my two functions in this vector so far, my ball object so far is going to be a drawing function, so it'll draw itself. I've used the this word here, which means it's going to draw an ellipse based on this object's position .x. This meaning the ball that I'm talking about, then the pos, then its x value. Sarah's doing dot products component-wise, yes. Not so fun. Lucky we have vector 2D. So this is just going to draw a red circle on the screen. Then I've got another function so far unfilled for updating its position. And what I want to do in my sketch is have a function add code to this function so that the ball will move in a natural way according to its velocity. It should bounce and it should act as if there was gravity in the scene. So, first things first is a draw loop. I didn't have that in the previous skeleton. This will draw the ball and then update it. So all it will do is draw it and update it. I might just put this into an editor. I think I had a open. Oh, cool. There's my ball. Okay, so far, wow. By the way, I have a new keyboard today. Ooh, keyboard. I've used a keyboard like this for a long time, but this is a new version of the same thing. and they've swapped some of the keys around, so I'm a bit confused about what I'm doing, but I should be okay. So there's my red ball. And the first thing I want to do is make this red ball move across the screen. So I've got its velocity, which is a vector, and I've got a position. So every time I call update ball pos, ball.update ball pos, I want to change my position values according to my velocity. And all I need to do to change them is add the velocity. So the velocity could be measured in pixels per frame, I guess, because I'm adding that many pixels to the X and that many pixels to Y every frame in order to get my ball to move. So now my ball moves. And if I want, I can change how fast it moves. And it just moves right off the screen. So that's no fun. It's not going anywhere useful. What I'd like to do first is get this ball to bounce off the edge of the screen. So when it moves to the edge and my pos becomes less than 0 in the Y dimension, I need to do something. And what I actually need to do is that when I detect it moving off the screen, I'm going to times one component of the velocity by -1. So if it's moving off the top of the screen, I need to change the velocity, the Y dimension of my velocity vector, into its negative version so that it moves the other way. Similarly, when moving off the right side of the screen, I should be multiplying that by -1 so it moves back this way. So I've got a little example about how that would work right here. So if this dot pos.x greater than width, or this dot pos.x is less than 0, then this dot vel.x times equals -1. So I'm just going to invert the x dimension of our velocity, and I'll pop that into my editor. And I can do it all in the same place. All in the same place. That's pretty cool, right? So I can first update my position, then check the boundaries, and implement this bouncing behavior. So let's see if it works. Bounce, 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 bounce. It seems like my ball is working. I'll just move it in another direction. -2. That's pretty cool. It just seems to be bouncing. This is not a perfect implementation. I'm sure you folks could improve it vastly. It's just one that I came up with in a few minutes just to demonstrate the point, the simplest possible one. Sometimes the ball gets stuck outside or off the screen in some cases if it moves too fast and can't get back in before its velocity starts flipping back and forth. Yeah, so I've got a bouncing ball, but it bounces forever. I want some kind of force which is going to change or cause it to move in a way that we expect it would in the real world if it was a sort of an up-down bouncing ball. So what I really want to do is add gravity, imagining that the top of the sketch is up and the bottom of the sketch is down. So gravity is a constant acceleration towards the ground. And what that means is that rather than changing my position every frame because of a constant velocity, I'm going to change my velocity every change because of a constant acceleration. So all I have to do is add a change in velocity in the y direction only because of gravity. So there we go. This dot vel.y plus equals 0.5. Let's make sure I get that in the right place. Update gravity. Oops, now my ball falls to the ground. Up, 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 and bounces. So it's acting like a real ball now. I see now where it gets stuck. I'm not going to worry about getting things exactly right. I guess you should sort of prevent it from moving off the screen and I let it go a bit too far. And if it goes off the screen with a low velocity, then it gets stuck. Oh, cool idea. Math.abs velocity. I could add another force. So far I've only got a velocity due to gravity. I might add an extra field. I'm just going to add acceleration. Creates vector. Spelled it wrong. 0, 0. So I'm starting with 0 acceleration. And, well, it's always going to have... Oh, no, I don't want that. This dot ac. This dot vel dot y. Oh, I need to do add. I wasn't going to add a gravity well. It was too hard for me, Ben, but you can show me how to do it. I won't add a whole acceleration vector there. You could do that if you wanted, but I think I might add one more force. So maybe I'll add wind, pushing things to the left. So this dot vel dot x minus equals 1.0. So it's always getting pushed to the left. That's a really strong wind. I can make the wind less strong, 0.8. And maybe I could make invert gravity. So now it's going to be brought to the ceiling instead of, it's a helium balloon instead of a ball that bounces on the ground. Yeah, okay, so that's all I'm going to say about forces in this lecture. But we will come back to some of these ideas in one of the later examples. Doing the little gravity well is a cool extension to that. I think there's a nice example in P5. Oh, what's forces example? Oh, it's a lot of things. Ooh, they're moving underwater. So we've got balls that bounce on the ground, that they have gravity, but then when they're in this gray area, it's like they have more friction, so they slow down. That's cool. This is a more complex example. It's got drag being implemented. Yeah, so there's lots of cool ways to extend this idea. Particle system, what was that? Oh, it's a lot of those guys, particles. Just gonna have a look at some double pendulum. Yeah, sorry, I'm not going to do a double pendulum example for you. Maybe next time. Maybe next time. Okay. Moving through some more examples. Here's a complete example. Feel free to have a look at this if you haven't tried this kind of thing already. Have a crack with it. So, the next thing I'm going to talk about is this example called Game of Life. Which is a simulation which is, I guess, less realistic than the previous one. The previous one, we're trying to examine some situation and make it act like it would in reality. In Game of Life, we're trying to take a situation which would be an ecosystem and make it act in a way that is interesting and emergent, but maybe not realistic. So it's an idea due to this guy, John Conway, a famous mathematician who was really into recreational mathematics and computing. He came up with this idea of Game of Life that was kind of published as a thing you might do with pen and paper, but people got interested in doing it on computers. It's a very simple idea, so it's not like this is something that it takes hours to understand. It's just a little zero-player game where you set up a grid of little blocks and they just have some behaviors that emerge over time as they change. Sadly, John Conway died in January 2020 of COVID-19, in fact. So this terrible pandemic touches us all in different ways. So Game of Life is an example of a class of simulations called cellular automata. Cellular automata are kind of a way of representing a complex phenomena in a simple framework. And the simple framework is that you have a list of cells that can have a state. You can represent them by a grid on graph paper, for instance, but they can also just be represented as an array in the computer. So cells live on a grid. Now each cell has a state. In our case, we're using true or false, but you could use 1 or 0 or up or down. And then when you draw a diagram of your cells, like in this example here, we could be coloring them in and making them darker if they were true, or having them white if they were false. So then each cell has a neighborhood of adjacent cells. So if that was, where's my mouse gone? My pen, sorry. If this is a cell I'm interested in, then it would have a neighborhood of 1, 2, 3, 4, 5, 6, 7, 8 adjacent cells. That cell being a true, these ones being true, those two being false, these three being true. Now the trick with cellular automaton is that you then define some kind of rule which will allow cells to change state. So you'll say, okay, in the next frame of my simulation, all my cells are going to change state according to what their neighborhood looks like. And you could have any rule you wanted, right? It could be that this cell becomes true if its neighbor number 1 is true, right? Whatever is in the top left corner is true, that cell becomes true as well. That's a very simple rule, but you can do whatever rules you want. And there are lots of cellular automata. It's a very early idea in AI and computer science to start exploring these things. But we're talking about this particular one, Conway's Game of Life. This is a 2D CA, a 2D cellular automaton. There are 1D ones that are just in a list of cells, but in this case we've got a grid of cells. And what's going to happen, what's going to happen with our cells is that every state we're going to update them. We're going to say if that cell is true, then it's called alive. And if that cell is false, then it's called dead. We're going to say that if a cell is alive and it has more than 3 neighbors, then it dies because of overpopulation, right? If it's alive and it has less than 2 neighbors, then it dies because of loneliness. So a lot of death so far. But if it's dead and it has exactly 3 neighbors, then it comes to life, birth, right? This is a very weird life form. It requires 3 parents to come to life. They're not the standard number for us. So those are the 3 rules, very simple rules. Oh, of course, if it's alive or dead and it doesn't meet any of these, either of these criterion, then it will just stay the same. These are just the change criteria. So what are we going to do in P5.js to make this work? Well, we're going to need a 2D array of Boolean values. We're going to need to draw an array on the screen at each frame. We're going to need to find out how many neighbors a cell has. And we're going to need to update the array at each frame according to the rules. Now, I know normally I sort of take examples from scratch, but I'm trying to get through a few examples this lecture. So I've got one that I cooked up earlier, working with Dan Schiffman's book. But which one is it? That one? No. Probably this one. So in this example, I've got an array here for the cells. I've got another array for the cells in the next frame. I'm going to calculate it that way. 2 vars for my rows. I'm just going to start with a small simulation. We'll go show you how it works bit by bit. So the first thing I need to do is fill up my array of cells randomly with some starting numbers. So I've got a function here to do that, fill cells randomly cells. and that is just going to loop over my array. Now my array at the moment, I only run this when my array is completely empty, so it could be problematic if we tried to do this again, but assuming C is an empty array, I suppose I could change it so that it just updates that variable. I don't need that there. Fill cells randomly. Let C equals that. So I'm going to start with a blank array. I'm going to iterate over my number of rows. Then each row is going to start as a blank array. Then I'm going to iterate over my number of columns, another for loop. And then I'm going to add a random value into that cell. Random between either true or false. So what will happen is that I end up with a two-dimensional array where everything is either true or false. And I might just print what I get, so we can see what it is. Now cells, not cell. So here's an array. It's an array of arrays of size 10. This array is false, 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 false. I'll tell you that detail why that's the case. Next row has one true in it. Row after that has a lot of trues, etc. Now, one thing I've done is made sure that the outer border of my cells is all false and never changes to be true, because I'm lazy. So I'll tell you why that's the case in a minute. Let's draw it. So drawing this is going to be pretty easy as well. I'm going to draw my cells. I just figure out what the width is for each little cell rectangle. That's going to be width divided by the number of columns, and the height for each little rectangle. Then do the same kind of thing. Go through all my rows and columns, and then slowly, I don't know why I've got a row there. What's that used for? Wouldn't even know. I don't think I need that. 2 for loops, I and j, I for rows, j for columns. And then I choose if this cell Cij is true. I don't need to put equals true because it's a truth value. I can just use it directly in an if statement. If that cell contains true, then I will fill it with gray. And if it's false, I will fill it with white. Then I draw my rectangles. So that will draw my starting pattern. So then I need one more little helper function. I'm just going to close these ones up. Fill cells randomly and draw. They're working. Every time I run it, it should have a new starting pattern. Then I need to figure out, if that's a given cell, I need to figure out how many of the neighbors are true or not, and then just get a number out of that. So I've got another helper function, which takes my cells, that's a 2D array of cells and a location, and tries to get all the neighbors. I'm just going to be really, really dumb about this and just do 8 checks and then add to a neighbors variable. So let neighbors equal 0 if c I minus 1 j minus 1. So if that's ij, then I minus 1 j minus 1 would be this value here. If that's true, then add 1 to neighbors. If the next one, which would be that one, is true, add to neighbors. If this is true, add to neighbors, etc. 1, 2, 3, 4, 5, skipping the cell I start with, 7, 8, 9. So that would give me all 8 neighbors, adding them all together and returning that value. So now I have a neighbors function. Now you see why I might have left these borders white or false, because if I was on one of these borders and I checked it for a value, then I'm going to be looking for values outside of my array. And I'm just too lazy to bother doing sense checking and figure out if that works. So I have ignored that case in this very simple implementation of Conway's Game of Life. So this is the getNeighbors function, and that'll be used in our update function. The last function we need is going to update my cells according to the rules of the game of life. So I'm going to apply the rules. This is the bit where I apply the rules. So what I do is I loop through all of the cells. Actually, I'm looping through all the cells which are not on the border. So starting from I equals 1 and going up to I less than rows minus 1. Then I figure out what the neighbors are for that particular cell. Then I figure out what particular value that cell currently has, S, its state. And then I'm going to make a new variable called sNext, which will be the next state for that cell. Then I apply the rules. So if S, so that means it's alive, and n greater than 3, then sNext equals false. So that's the overpopulation criteria. Else if S is alive and n less than 2, sNext equals false. That's the loneliness criteria. If not S, so if S is dead, and n is exactly equal to 3, then sNext equals true. That's the birth criteria. Finally, if none of these are met, then sNext equals S, so stasis. And then I change next cells ij to be sNext. And finally, the final thing after I've gone through the whole environment and updated everything for the next frame, I finally change over the cells that we're looking at for drawing. So that's my update cells function. Now I'm just going to run this really slowly, 1 frame per second, so that we get an idea about what it looks like. So here's my little game of life unfolding. I have to say that I'm not completely certain I've got the implementation right here. This was a quick game of life implementation, particularly this one. It's gone now, but if there are 3 in a row, they should move and be like a little propeller. Like that one didn't work. So I've got something wrong here. Now there's something with the game of life, which is that there are known to be some patterns that are static. This is one of the static patterns called the box. I think it's called the box. If you look on the Game of Life Wikipedia, there's lots of examples of static things, or the block, the beehive, the loaf, the boat, the tub. They're things that are still. There are things that oscillate. And there are things that are called spaceships which move across the screen. So these are all emergent phenomena from the Game of Life. Where's my Game of Life? Stay on page. Let's speed things up, or actually let's make it bigger, 20 by 20. And speed things up to 10 frames per second. And see this run a bit faster. Yeah, so I think I've got it wrong, but I'm not quite sure where. You folks can look at my code and figure it out. There's my slides. Yes, the reason I think I've got it wrong is that normally, if we look at the one that Dan Schiffman made, it turns into, it sort of starts to disappear really quickly. And there's some of those blinkers and a block. A couple of blocks, there's a boat, there's a beehive, there's some blinkers. So I don't think I'm quite doing the Game of Life correctly. Please tell me what is wrong with it. And you know, I don't know, you won't get anything, but you'll get an official comp1720 thumbs up if you can figure it out. Next thing, and last example in the last few minutes, this idea of Boids and flocking. Again, this is from a particular computer scientist, and again, this is quite an old idea. This is by a popularized and invented or written down by a computer scientist called Craig Reynolds in the mid-80s, 1986, to do with doing computer graphics. And Reynolds was interested in simulating animals, groups of animals together. So you're simulating a flock of animals that would work to behave together like a flock of birds or fish, and maybe avoid obstacles or exist in a scene. And he wrote down this concept called boids, of a very simple simulated animal that would be represented by a little triangle. Here's a little flock of boids as a kind of generic creature. And this is widely discussed as an example of artificial life. Artificial life sounds like a wacky term, but it's a real research area. And there's a conference called A-Life and a journal called A-Life. I went to it once. It was pretty cool. People thinking about computer simulations of life and emergent behaviors. It was a very artistic field of computer science, or a very scientific field of computer art, I guess, as well. So what you do with boids, the first boid exercise, I guess, is to implement 3 simple behaviors that called separation, alignment, and cohesion. I'll talk about those in a minute. But from those simple behaviors emerges a very lifelike behavior, and something which is quite fascinating. So here's a boid. It's got a direction and a velocity. So its direction is the direction it's pointing. And I guess the velocity is the length of this vector. So it would be faster going that way. V, and then direction is theta. This boid can react to other boids in a small neighborhood, so it can figure out what boids are around it. You program it to do it, of course. And it would also know their direction and velocity. So here's the 3 rules, and I've just borrowed Craig Reynolds' diagrams for this in my SOO, Craig Reynolds. First rule is don't crowd. So, I think I had a better version of that slide. Yeah. Don't crowd. So if you're going in this with a couple of other boids and you're very close to them, you should adjust your heading to kind of take you away from those nearby boids so that you're not all overlapped. And then if there's a lot of boids around you, you should try to move in the same direction. So you do this by finding all of the movement vectors, all the velocity vectors of your local boid neighborhood, and take the average velocity of that, and then try to adjust your velocity to approach that average. And then the third rule is cohesion. So you're trying to, if you've got a boid here, you'll want to move to the kind of centroid or the average position of these other boids. So try to move your heading so that you're moving towards that average. And all of these things have little details or how much you do them that can be adjusted to give your boids different behaviors. So I've got a boid demo. I will show you now my boid demo. Again, I took a lot of inspiration from Dan Schiffman's boid demo. In fact, I just took his code and modernized it a little bit into current JavaScript standards, and just to make it make sense to me. So there's 2 objects or 2 classes in this code. I know we haven't talked about JavaScript classes in this course. I guess the short answer is that if you're a computing student, you won't have to have me explain it to you. If you're a art student, you'll be thinking, am I talking about like another course I would take? No, a class is like an abstract version of an object or a design for an object. So you get a class which is like the class of cars, right? A class of cars would be a mental model for what a car might have. It might have 4 wheels, 4 windows, a windshield, a back windshield, a boot, and an engine. But lots of cars fit that description. So it's a design, looser design for an object. And then when you make an object from that class, it gets all of its details filled in. So our class for our flock is going to contain an array of all of our voids, and that will just hold them all, excuse me, hold them all and allow us to update them. And then here's our class for void. The reason I need to use classes here and not just objects is that in this example, I need to be able to make a lot of void objects. So we need the class to be able to be this kind of abstract plan for it and then make a lot at the same time. So we use this special function called constructor, which sets up our object to start with. So it will create an acceleration vector, make a velocity vector, make a position vector, really similar to our ball example. It's got an R, which is the size of it, the radius, according to, this is the way that Schiffman has done it. It has a max speed and a maximum steering force, so they can't steer too quickly. They can only be moved at a certain rate. Then similarly, it can do things to itself. It can flock, it can update, it can make sure it moves across the screen, the borders sort of takes it to the other side of the screen if it runs off, and we can draw it. So the drawing is easy, that just makes a little triangle, begin shape, vertex, vertex, vertex. The trick here is the flocking rules. I'll tell you about those in a minute, but yeah, Ben, you're absolutely right. You can make a lot of objects in a loop. I guess I could have done this without classes, but it just would get a little bit wild. Maybe I can think of a classless, a not classy way of doing it, but I do like to do things in a classy way, so, you know. So I've got one void in my example to start, and it just is going to sail along in a random direction. Every time I start the sketch again, it has a new direction. And when it moves off the screen, it comes along on the other side, which is cute. So the trick are these three different behaviors. So here's, I've made a few more by dragging with the mouse. Again, Dan Schiffman's good idea to do that. And they're acting as a flock, but this one's not, because it's not ended up in the neighborhood yet. But if I put some more next to that one, they join up because they've detected they're in the same neighborhood. Whoop. And then when they move past each other, they start to pick up some stragglers. So the three rules for voids, they were separates, alignment, and cohesion. They're all a little bit complicated, so you can have a look in this code and understand them. It's basically trying to calculate an average position or velocity of the other voids and then adjust the direction of our main void that we're holding in our hands a little bit, but not too much. There's a few little details with special magic numbers and something like, what was it? It's called here. Implement Reynolds steering equals desired minus velocity, like some special ways of doing things that probably by trial and error Reynolds came up with. But it's a fun thing to try out. And what I think is cool about this example is that we get a lot of emergent behaviors that we find very unpredictable. Like, we're not exactly sure how these voids are going to react. They're going in lots of different directions, they're choosing different ways to exist. But where's the randomness, right? They're not making random decisions at any one time. The only time that we make a random choice, if I just search for random, is the initial velocity vector of each void. So they choose a random direction to start off with, and then after that, everything is just kind of integrated by these simple rules. And we find a system that has emergent and interesting behaviors, which isn't making random choices in every single frame. And I think that's something I see in our assignments and code, is that some folks are adding randomness in because they want those interesting emergent sketches. But if there's a randomness in every frame, then things just look completely random. So maybe it's good to start with randomness and then have rules to change your the behavior of objects in your code over time. So this is the little flocking demo. Of course, you can see it working correctly in the examples, I suppose. Flocking. This is Dan Schiffman's example with lots of little voids. Aren't they cool? I think other people have done things where there's flocking according to a kind of field of vectors. So there's movement according to a field, which is interesting as well, but this is a kind of random flocking. Yeah, so how shall I end? What is the point of doing this? Why simulate? Well, I think that this is where coding multiplies your creativity, because once you've set up a system with some rules, even if those rules are a bit tricky to implement, you get these emergent behaviors for free, right? So your artwork becomes even more interesting than if you were like rendering every single frame in Photoshop or Final Cut Pro or Premiere or Ableton Live or whatever. So these are things that you really can't do in typical like pro level creative software. You need to use a programming language to code up these behaviors, code up a system that can contain certain rules and can be updated over time. Then you get something that's really convincing and emergent. I just think it's fascinating how convincing this little example is. I mean, it's more complicated than I can really explain in detail in 10 minutes, but it's not too complicated for anyone in this course to understand how this code works. And yet it's really, really fascinating how it works. Yeah, so that is the end of my week 11 lecture. I'm now in question time. I've got a few minutes if anyone feels they want to ask a question. Oh yeah, I suppose I should say that the assignment 3 feedback went back. I did post on Discourse the mark distribution and the mark statistics. By and large, people have done really interesting and wonderful social media ads. I think it was quite a hard spec for some people because it was more specific than the previous 2 assignments, and that caused some I don't know, some challenges in terms of finding an idea which was useful. So, but again, the marks were great. Everyone did acceptably acceptably well, I think, depending on people's level. So that leaves you with one more lab, one more lecture from Tony, one more from me, and then one more from Tony, to get to the end of the course, get to the end of week 12 and get your major project in. I hope that there are lots of more questions about it over the weekend on Discourse. I know this is a very busy time of semester, but I'm very glad that people have done at least one sketch of their major project and had a few chances to chat about it with their tutor already. And of course, as always, let me know if you have any issues or comments. So maybe I'll go. I'm not sure who else is watching except for Ben, but catch you folks next Wednesday, and good luck with all of your week 11, 12 stuff happening at uni. See you later. Outro.